Hey, welcome to video 4 in our little mini series on probability measure. This one is on measure spaces. Now, the first 3 videos we looked at set theory, then fields, and then sigma fields. And then once you developed a sigma field from a universal set, then that tuple creates what's called a measurable space. You know, that's the structure around what probability measure is developed on. And I wanted to look at the most popular, or in my opinion, the most popular measure space, and that's called the Borel sigma fields. And that's going to be pretty much the assumed sigma field that we're going to work under for the rest of the talk here, or the little mini series. And I'll be more specific and highlight everything as I go in each little video. But let's just jump right in. This is the Borel sigma field, and really we're talking about over the real line. So our universal set is R, the real number line. And we're going to define a class of subsets of S, which is all possible intervals in the real line. Okay, and this is the case, and this is so we have open intervals from x to infinity, closed from x to negative infinity. We have every possible type of interval where x and y are in R and x is less than y. So, infinite number of these types of intervals. Okay, so this is a subclass from our universal set. So now, if we generate all possible sigma fields from S that contain this class C0, and then take the intersection of all those sigma fields, that's what the Borel set is. So it's the sigma field generated by this class is called the Borel sigma field. Okay, so now I'm going to go through one theorem here, and that each of the following classes generate the same exact Borel sigma field, which is a little surprising to me, but it does, and we'll prove one of them, and then the others are very similar. So class 1 is all intervals of this type. Then, if you take all the sigma fields from S that contain C1, and then take the intersection, that is going to generate this same sigma field. Okay. But notice that class 1 is smaller than class 0. So class 1 is a subset of class 0. But yet they generate the same sigma field, the same Borel sigma field. And then this is the same, it's just a different type of interval. And if we go through each of these, it's really the same thing. They all generate the same Borel sigma field. Again, just a different type, all the way. Okay, and so the sigma fields generated from each of these classes ends up being the Borel sigma field. Okay, so now we're going to try to prove number 7 here, where this is the interval. And before we start, I have to make a note here that if this subclass is a subset of C prime, then remember, these are 2 classes of subsets of S. Okay, so then if we generate all possible sigma fields that contain C prime and then take the intersection, that generates a sigma field. If we do that for this smaller set, take all the sigma fields that contain C and then take the intersection, well, the sigma field here should be a subset of this sigma field, and that's true. That's what this is saying. Now, if so, this is a given. But if it ends up that this subset or this sigma field is a subset of this one, and that's what this is saying, then they have to be equal. So if this is a subset of this, and then the sigma field associated with this one is actually a subset associated with this one, then they have to be equal. Okay, and actually this is one of the points about set theory that I find intriguing that you have to apply logic in a lot of the proofs, not just, it's not everything is a serious mathematical statement. It's sort of their logic statements. But anyway, so to show that this generates the Borel sigma field, if we can show the Borel sigma field is a subset of the sigma field generated by C7, then we're done. And this is because C7 is a subset of C0. So that this sigma field is actually a subset of the Borel based upon where we start. So if it ends up that this is a subset of that, then they have to be equal. Okay? So now, one more step before I show you the next one is, now this sigma field here is a sigma field that contains all sigma fields that contain C7, which is this type of interval. And then we take the intersection. And then this one is the sigma field that contains, class C0, which is all those sigma fields. We take the intersection. But so if we can show that class C0 is actually in this sigma field, that's another way to show that these have to be equal, because this is the smallest one possible that only contains C7. But if it also contains C0, then that sigma field and that have to be equal. Or this is a subset of that, I should say, which means they're equal. And so that's what we're doing here. So if we can show that the class 0 is actually a subset of the sigma fields of C7, then that says the Borel sigma field is a subset of this sigma field. But because we started out with this arrangement, then those two sigma fields have to be equal. And this argument here, you may have to rewind and make sure that is right in your mind. But that's what we're going to show here. Okay, so now let's let xn be a decreasing sequence to x. Okay, so then every interval of this type is in the sigma field C7. And that's by default, because that's the type of intervals that are in C7. So those all have to be in C7. But since it's a sigma field, this countably infinite intersection also has to be in C7. But that, since this limits down to x, this is the result. So that also has to be in C7. But this is one for all x, and this is one of the interval types in C0. So now let's go to the next one. So since this is in the sigma field generated by C7, its complement has to be in this sigma field, which is this. So it's also part of the sigma field. Well, this is another type of interval in C0. Well, these intervals are always in sigma field generated by C7, so the complement has to be in it. And this complement is this, which is one of the types of intervals in C0, but it has to be in C7. And then we just go down. Now this type, which is here, we know is in the sigma field of C7. And this we know that because that's what C7 is, so their intersection has to be in it, which is this type of interval. So it's in the sigma field. And then we keep going. We know that these two are in sigma field associated with C7. They're generated from C7. Their intersection is, which is this. The intersection of these two types is this interval, which is in the sigma field. The same way with these, which is that. So that says the class C0 is in the sigma field generated by C7. So that says that the Borel set has to be a subset of this. Well, if that's the case, then they have to be equal based on the logic that we set out to begin with. Okay, so that's a little proof of the Borel sigma field, or that these generate the classes 1 through 8 generate the Borel sigma field also. So now let's look at a two-dimensional Borel sigma field. So let's let S be this cross product. So it's like the XY plane in a sense. And class 0 is all the rectangles in R2. So, you know, this interval cross this. So, you know, it's, if you look at that on the R2 space, you know, we're generating little rectangles, and you go through all, and I'm dot, 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 because I got a little bit lazy of going through all the types. But you have to think about all the different types of intervals, all rectangles in R2, such that these conditions are met. And then you generate a sigma field from that class, and that's called the two-dimensional Borel sigma field. Okay, so now we can also do that with k dimensions. So if we have a k-dimensional Borel sigma field, we let S be this R to the k. So it's the cross product of k different, you know, intervals in R. And then you know, where C0 defined similarly, then we find all the sigma fields that contain it, take the intersection, and then that's the Borel, the k-dimensional Borel sigma field. And so why in the world is this useful? Well, this is the structure that's needed for random variables. Okay, so for this, or the one-dimensional Borel sigma field is random variables that we like, the Poisson, the normal distribution, you know, where it's a random variable. Where this one here is a two-dimensional Borel field, that helps us generate like a bivariate normal or bivariate Poisson distribution. And then this is a k-dimensional random variable. So these are setting up the structure for us to find probability measures and then eventually random variables on these structures. Okay, and then before we go, I want to talk about some sequences, monotone sequences, limits, etc., and then we'll be done for today. These I think will come into play a little bit later. The last result I give, I'm not quite sure if I will, but it's interesting and used a lot. So if we have a monotone sequence of, say, AN, it's increasing if the previous is always a subset of the next. Okay, and it's denoted by AN increases. So for each number, it grows. It can be equal, but it never gets smaller. And the same way in decreasing is just the opposite. Every sequence gets a little smaller. So, and it's not saying that this goes to infinity or this one goes to 0. They may, but they're just increasing and decreasing. Okay, so then the limits of these sequences, of a monotone sequence, if AN is increasing, then the limit of AN can be thought of as the union of all these sets, because each set gets a little bigger, a little bigger, a little bigger, a little bigger. So really the union is determined from that last set, you know, and so the limit of that is really this union. And then the same way, if we have a decreasing sequence, the limit of it is the intersection. And because each one gets a little bit smaller, the limit really depends upon the last one, or the limit of this, and so that it can be rewritten like this. So now we have, for any sequence, we have what's called the inferior limit, which is defined in this kind of weird way. It's the limit of the infimum of A, which is the union of the intersection of AJ. Okay, and I'm gonna leave it vague. If we ever cover this again, which there's a good chance we will, then I will go into a lot more detail. And then we have this superior limit of A prime, which is the limit supremum of AN, which ends up being the intersection of the union of the AJ. Now, these here, what the inferior limit does is, if you know, whatever this limit of AN is, this grows it from below, so it goes and then finds it. Where the superior limit, it starts big and goes and then finds the limit. But if so, that means that this inferior limit is always a subset of this superior limit. And if our sequence is monotone, then those three limits will equal. They limit to the same thing. Okay, well, that's all I have for today. I hope you enjoyed it. Next, we're going to look at actual probability measure. Then after that, we have conditional probability, independence. We have random variables, which is a pretty intriguing video. Distribution of those random variables. We might get into the accumulative distribution of those random variables. So we have 3 to 5 more little mini videos to discuss of this mini series discussion probability measure. So, well, if you liked it, please like it and subscribe so you don't miss the next one. Thank you. Bye.